Good afternoon, everyone. We are in such a big number. Kind of to be expected. Most people are traveling, but we have a recording. I am not traveling, so I was like, I'm hired to work, so I should come here. So thanks everyone for coming. So where we started last time, it's so weird how my voice is louder now than there are so many people. I'm not used to it. So I said, we learned the full development of large language models, right? Like we know every single stage of even the most recent language models that have been released recently, like Gemini 3 and Alma 3, and I think the new Claude has been released recently as well. So we have a very, very good mental model of what LLMs are. And this course has focused on using LLMs as a general model for lots of NLP applications, for translation, summarization, classification, retrieval, and whatnot. And the topic I want to kind of finish with is, in terms of LLMs, is how can we use these LLMs efficiently both at the inference time and then in fine-tune them. So we are going to talk about that today and then again on Monday, most likely. Before we jump into how to efficiently do inference and how to efficiently fine-tune in terms of the speed and memory usage, specifically GPU memory, I do want to go over a little bit of kind of decision-making about how you can approach using LLMs for various tasks you might have at your jobs. So the first category, the first dimension of which you can think of is classification versus generation. Classification tasks are, remember, tasks like sentiment classifications, where given a piece of text, you need to assign some category. And text generation tasks are those that are inherently tasks where you need to produce text. Although we have seen in this course, you can also approach classification as text generation, where you generate the string resembling the class, such as positive or negative. So let's say you have a classification task and you decided, okay, I'm going to use some LLM-based approach, right? Like I'm not talking about any other approaches that might exist out there except LLMs. The first thing you should ask yourself is whether I have labeled data or not. That's the first thing you need to ask yourself. And if you don't have labeled data, you also need to ask yourself how hard would it be to. If your data labeling is not super demanding on a participant or an annotator who will label the data, and if you are in full of resources, your boss says, like, feel free to use a budget for labeling data, that's an important consideration to have, because you might be doing all sorts of weird things to kind of overcome the problem of not having data, when solution could have been, well, just annotated and fine-tune a model. If you have labeled data, you can fine-tune a model, right? Because you have supervision. And generally, if you want a model that is best for the task at hand to be like a very specialized model, there probably is no better solution than to fine-tune a model using labeled data. That's going to make a model use all of that knowledge it had acquired from previous stages of LLM development, while also be extra specialized for your class. So if you really care about having the best performance for some specialized task, I can't imagine better approach than fine-tuning a model. And now, because we have a task that is inherent to classification task, you have options. You can use those encoder-only transformer models like the Bertha or modern BERT. You could also use decoder-only models, right? And you can also use encoder-decoder. The only difference is if you are going to use new classification head, remember that, or you are going to reuse the language modeling head. Of course, reusing the language model head is possible only with transformers that do have encoder components. So you wouldn't have that option for the encoder-only model. If you have a ton of data, I mean, it's hard to say what is a lot, right? But I would say if you have thousands of labeled instances, I would say that having a new classification head can be the smoothest approach, because then you don't need to deal with, oh, the model has capacity to really answer in all of these different ways, so I need to constrain the generation by giving demonstrations and whatever else we were doing. So giving just a new classification head that's initially random, but then it's changed during fine-tuning could be a pretty smooth approach, which gives you really good accuracy in label data. I can't tell you exactly which approach, which model would be the best, and no one can. What you're doing is empirical, both empirical science or empirical engineering, where you need to try a bunch of versions and see what the accuracy or F1 score on the development set is, and then one of these runs will be the best, and you say, okay, I'm going to use this model and test it on my test set. Okay, however, we have also this situation where you don't have labeled data. Labeling data would take you a lot of time, or you simply don't have the many experts that could label the data. Labeling data simply is not something you can do. Then you can prompt models, right? We have learned that large language models are extensively instruction fine-tuned. They're ready to follow many, many, many instructions. So prompting is something we could use here. And here you will likely use encoder, decoder, or decoder-only model, because those are, and I would say honestly today, even encoder, decoder, FLANTY 5 is outdated. So most likely you are going to use decoder-only pre-trained transformer that's best right now. For example, I was thinking, what could I give you here as an examples? Olmo 3 instruct RL, Quen 3, Gemma 3, Llama 3.1 instruct, however it's called. These are good options to prompting if you're using open models. And then with proprietary models, obvious suspects, ChatGPT, Claude, Gemini, right? Okay, and then if you are doing prompting, you have no other options, I should say, than reusing the language model. Because if you don't have data to label data, then if you had added a new classification head, it will be randomly initialized and you will not have data to tune its parameters, right? So you must reuse the language modeling head when you are doing prompting. And now, if we have tasks that's inherently generation task, we know that the only option that's not great here is fine-tuning encoder-only models, right? Everything else is the same. The only reason why we're going to use encoder-only models is because they are generally not trained with the language modeling objective. And because they are not trained with the language modeling objective, we have seen empirically that they are not good at next local prediction because they have never been taught to do that. And they are never going to be good competitors to decoder-only autoregressive models. But everything else, the logic kind of stays the same. Okay, so there is that. Remember, for prompting, you had 3 different but very similar kind of main approaches, which are zero shot. You just give some instruction, you give an instance you want the model to classify or generate new text for. Then we have in-context learning, where we give few demonstrations of the task, where we actually show how we would like the model to do the task for those examples. And then chain of thought prompting, which is just a way to elicit verbalization of model's reasoning by telling it, let's think step by step. And then we have seen last time how new age LLMs like Olmo 3 have extensive instruction fine-tuning for generating chain of thought. So they have been extensively primed and developed to provide these kinds of verbalized reasoning. So if you do write something in your prompt along the lines, let's think step by step, they are going to give you verbalized reasoning. And then if you take my interpretability course, we are going to talk about how that verbalized reasoning is not necessarily faithful to internal computations of the model. I want to also, when I talk generally with people who are not using LLMs in their daily jobs, but they would like to, one consideration to have is the programming expertise. And most of you here are CS majors. I would say that for you, fine-tuning a model, although I haven't forced you to do it, I expect that all of you could easily do it. So I don't think this kind of consideration matters so much for you. This is maybe more if you are consulting someone else for what they should do. But if you are choosing between open weight models and fine-tuning, or using a much larger proprietary model and just prompting, they could have roughly the same performance, right? Like fine-tuning general is good, but when I said it's better, I meant everything else kept fixed, right? So if I have, let's say, 32 billion model, and if I fine-tune it for the task or prompt it, with fine-tuning, I will get more performance unless that task has been so extensively covered in the instruction, fine-tuning, like sentiment classification is, for example. So sometimes for someone who is not so versed into babysitting these GPU jobs, it might be easier for them to just spend some money on APIs and get inferences out. So using APIs also requires a little bit of programming, but it's honestly just a few lines of code and just know how to process your data. With open weight models and fine-tuning, you need to, you use Quantization ecosystem. You already have so much code to do. Honestly, there isn't much code to be written even there. But running jobs on GPUs can be, I think, daunting for people who haven't, run jobs and service. Google Colab we have used it for backend systems has GPU access, but how long you can get the GPU for and whether it's available basically depends whether you have premium account or not. So it's a great, I think, for prototyping, but I wouldn't imagine that someone would build a full-on or fine-tuning solution in a Google Colab. So yeah, something to keep in mind on for you. I wouldn't say this is a serious consideration, but if you are consulting someone, this is something to consider. And then finally, you might ask me, why even bother with smaller open weight models when proprietary models and prompting them gives good results? I think the main argument I will always say is they're simply cheaper because they're literally free, right? So if you have GPUs at disposal, and you can fine-tune a model, or just, you don't even need to fine-tune it. You can also just prompt open weight models, then they're free, right? Like API will also always cost something. Another thing to consider is that you have access to your data. And although today corporations like OpenAI offers, business models and they promise that want to keep your data safe, I think it's a really hard promise to make. And just as an example, here in their own paper, when they written GPT-3 paper, they said that they had a bug and that they accidentally trained on all the data they shouldn't have trained, all the tests. So, seeing how doing this engineering jobs is really hard. I don't think these, engineers had any malicious intent or anything like that, but it's really hard to work with data of this scale and things can happen. So if you are working with medical data that's HIPAA protected, you might not even have a choice, but the data has to be on a specific, very specific server, which means that your GPUs need to be on that very same server. And then with open weight models, you can do more of interpretability because you have access to the model weights. So you can do interventions not just at the inputs, but also at the models if you want to inspect how the model would react. And another annoying thing is that proprietary models get depth. So for example, most The most recent example that upset people was when GPT-4o was deprecated, and people loved that model, didn't really like GPT-5. That's more for daily use and less, I would say, serious than when you do research with these things. And now no one can reproduce your study because the model you use is not out there anymore, right? So no one except OpenAI can reproduce your results, which makes for not so robust science as we'd like. So for this reason, if you care about reproducibility, you would maybe want to choose models that can't get, if you have a copy of a model, no one can take it away from you, right? I mean, there are always means, but in general, no. Okay, so these are kind of things I wanted to mention before we jump into how to use models efficiently. Are there any questions? Any decision making you are thinking you might need to make in the future that I can cover? I'm trying to also think what I didn't mention or mentioned previously. So last time we were talking about thinking or not thinking, reasoning LLMs or just pure LLMs. And, I've told you that in most cases, you don't need reasoning language models, although they are on the rage right now. So keep that in mind. And then if you are going to work with applications that have really long inputs, or you need to create very long outputs, then pay attention to whether there was a development stage of an LLM where that is handled. We have seen with Olma 3, it had quite an extensive stage just to handle longer sequences and to also generate longer sequences. Anything else that comes to mind? Yeah. No, I think I'm already making this course too machine learning key as it is. Yeah. Yeah. But I did say Kenny he should cover it in the agents for next semester. Yeah. Also, it's quite new, so when we teach, we come here with some sense of we know what we're talking about, but something was just released. We haven't had the time to engage with it ourselves as well, so it's a little bit hard to teach something that's like 3 days old. Although I'm giving my best, Okay, so yeah. This little recap of various decisions you will be making if you are using LLMs as a solution to your NLP problem. Also is a nice segue into, well, if that's your solution, how can you make generations come fast? Right. When you use ChatGPT, they appear immediately, right? Despite the models, although we don't know the exact number of parameters, but people speculate it's maybe even trillion of parameters. Okay, so let me talk a little bit about what kind of issues we face with efficiency. So now going through this whole course, you know that we work with these transformer-based models. They have so many decoder blocks. Each decoder block has various weights for linear projections and so on, right? So there is a lot of matrices where we store numbers, weights of our model. And there are also, as we are computing representation of a token, layer by layer, we create many of these representations or activations. So now also, most of you being CS majors, you know that to record or store one number in memory, you need, first of all, memory, but then we work with so many of these numbers that can accumulate and have very high memory demands for us. So memory is one thing. And we are not working with any kind of memory, but with VRAM, with the GPU. And we are working with GPUs because these graphical processing units have been shown at some point to be great for tensor computations. And tensor computations, which is core of our models, are much faster on GPUs than they are on CPUs. So you want GPUs because generally you can produce everything you are producing with transformers much faster and produce generations much faster. But to place your model on a GPU, you need a lot of GPU memory. And GPU memory is bounded. So even if you look at the most expensive US NVIDIA GPUs, like A100s, one has 80 gigabytes of memory. And I can tell you when I joined here, two of them together with all the other hardware cost $60,000. So that's a lot of money, right? And newer ones like H200s, which luckily also have CHPC, which have larger memory, 141 gigabyte, it's still not like huge amount of memory. One way you can think about how much gigabytes you need just to store the model is through this equation. So number of parameters, precision divided by A times 1.2. If we look at the model of 70 billion parameters, today, I would say a good model is 32 billion, so a little bit less is sufficient to get really good performance. But with 70 billion, you would need, using this equation, you would need 336 gigabytes of VRAM, which means that you would need 5 of these very expensive A100s or 3 of these even more expensive H200s, right? How many of you have access to a GPU that has 80 gigabytes or more? There is a hand if you do. One and a half. CHPC, right? This is a little bit of a trick question because, okay, not everyone is in the School of Computing, but everyone who is in the School of Computing has access to the CHPC. And CHPC, all of you can be on the SOC-NPU- whatever, SOC GPU NP or something like that is the name of the partition. So all of you do have access to A100s and H200s, but you need to beat all of my students to get into the queue, basically. It's a shared resource. Okay, so what I kind of recap of what I said here is that we need GPUs to have fast computations. Without them, fine-tuning and inference is too slow. But first of all, most people are limited with their availability. So, okay, you have access, but you still need to wait in a queue. And what you can place on GPUs is limited, right? Like even when you have access, for example, you have a cluster of 8 H200s on a new Granite cluster here at CHPC, that's still bounded, right? And there are certainly bigger models than collective memory of 8 H200s. Okay, so what can we do? How can we can't change the GPUs, right? We can't say, I mean, NVIDIA is going to increase the GPU memory for sure, but at a given time, you have, fixed number of GPUs and you need to work around that. So the question isn't how to change the number of GPUs. That's a different question. Rather, it's given the GPUs I have, how can I fit the largest possible model on these GPUs and get inference or fine-tune it? And I'm saying the largest possible because typically larger the model is within the same family. So again, everything else equal, larger model is gonna be better. That's kind of scaling law still showed up. Okay, so we kind of want to try to fit as much as we can. And the solution that's super typical today and that you will all use if you end up using LLMs in your jobs, in your research, is quantization, which is a method for compressing neural network weights and activations or representations by reducing their precision, by using fewer bits per parameter or per activation number. Now, I won't go over this. I'm just assume you all have your CS foundations. You know how different precision can be achieved. Our holy grail full precision float 32 is something that we would like, but something that takes too much memory. And the question is, how can we go into lower precision like int8 and still not lose any accuracy. So for example, here we have different Llama 3.1 models from 8 billion parameters to 405 billion parameters. If I recall correctly, Llama 3.1 405 billion was first open weight model that was on par with the proprietary model. It was so important at the time, but this scale was still like open community was like, great, we made it, but no one can actually use it except folks at Meta. So for such a big model, you would need almost 2000 gigabytes of GPU memory. And then when you do quantization, you are reduced to 243 gigabytes. And this is something you can easily fit on CHPC's compute. So today, you could actually, here at the University of Utah, using CHPC, use a model like this, but only if we quantize it into int4, which is way lesser precision. Okay, so people do that. We go from 2000 to 8-time reduction. So that might seem too good to be true. Like, what's the catch? What could go wrong when we go from full precision to int4?
Words having similar meanings would be represented as same, because for vector, suppose vector for king is 0.1, 0.2, or something like this, and you have 16-bit precision or 32-bit precision, you might have certain set of differences so which model can identify that this is king, this is queen. When you just lower it, probably there will be closer in vector space compared to what they were initially.
Yeah, so basically, if I make make a larger point out of example, the argument is by losing some precision, you need to remove some information, right? You are basically doing compression and you are kind of ditching some information. And if you're doing that, then the performance of the model may not be on par with a full precision version. So the challenge here is how we do this, how we go, we know how we can use quantization or whatever method to go from this method to that method, this precision to that precision. Memory is smaller, but how to preserve the information that matters for the model's performance. Okay, so I will show you the quantization that's done today, and it works. And it hasn't worked like when I started here, when was it, 2022, we didn't have good quantization, and it just randomly switched and it worked properly. And today, yeah, we all use it. It's a no-brainer. Okay, so in a nutshell, we have some float point range. Let's say we have numbers in this interval. What did I make up? 2.5 to 8.3. And we want to basically scale all those numbers into a set of points that are discrete points that are also within certain range, such as if we work with, what is it? Is this, this is, I forget which precision is this. Is it 4-bit or 8-bit? This is 8-bit precision, right? 2 to the power of 7.
Yeah, that'd be 8-bit.
Yeah, 8-bit. So if we want to, represent these numbers in this interval into 8-bit precision, we need to pick some numbers in this discrete numbers in this interval. And the question is, how do you map the floating point range into this integer range? And we are going to use a 4-step process that does that. And that's called linear quantization. It's going to have two flavors, symmetric and asymmetric. With symmetric linear quantization, we assume that the data that we are trying to quantize, let's say we are having weights, a weight matrix. We want to quantize it. So we want every number in our weight matrix to be mapped to some number between negative 128 to 127, if we are doing 8-bit precision. And with the symmetric quantization, we would assume that the mean of the numbers in this weight matrix is centered around 0. Now, without looking at the slide, is that okay assumption to make? What do you think?
Sometimes it'd be okay.
When?
I mean, obviously I see what it says on here, but I've seen it myself when I've looked
Okay.
at weights in models before.
Nice, yeah.
You know, I've looked at the min and the max and they're pretty much evenly spaced from one another. So one would assume that for weights, they definitely sort of fit within that centered on zero range.
Yeah. And that all comes from the fact that when we are training these models, we don't want instability, and instability comes when gradients become messed up. So for gradients to not become too large or too low or weird in any way, we typically normalize the value of weight matrices to have zero mean and roughly 1 for the variance. And this was achieved through layered normalization, which is written on the slide. So we kind of know that our weights should resemble this property because we have introduced this property ourselves into the architecture. But this does not need to be case for the activation. So when we get new token representation, that vector does not need to be zero mean or centered around mean, or centered around zero mean. Okay, so maybe today I will go into showing you asymmetric linear quantization, but the difference is honestly tiny, and we will have just one slide to see what you would change for symmetric one. So let's talk about linear asymmetric quantization. As I said, our goal is to take some, interval of numbers. So again, if we have a weight matrix, and if we are doing quantization of the overall weight matrix, we would take the smallest and the largest value in that weight matrix, and that would determine the bounds of the interval of numbers we are trying to scale to this interval, let's say again, negative 127 to 128. So given all the numbers in the weight matrix that are within this interval, we are trying to map each one of them in a limited discrete number of integer values. So that means that some portions of this interval will be mapped to the same integer, and this is called quantization bin. And basically that kind of hints on, well, you are losing some information. If these two numbers were, let's say, 0.002 different, with this quantization, we would map them to the same number. Then with quantization, we deem them to be the same number when originally they were not, and maybe the difference between them had more significant meaning than we thought. Okay, so to achieve that, to do this scaling, we are going to, as I said, use a 4-stage process, which is basically computing these 4 equations, and let's go into each one of them one by one. Okay, so here I had just an example, but I just said what I wanted to say. meant to say everything mapping to the same number with this example, but it doesn't matter since I covered all of that. Okay, so the first step is going to be to determine the range. So that's basically this blue interval at the top. So you take some values and you determine what the min and the max is going to be. One simplest way to determine the range will be to take the whole matrix and say, well, minimum is whatever is the smallest value in this matrix, and maximum is whatever is the largest value. In a slide or two, we are going to talk about slightly different approaches. And then for determining the interval for your quantized values, so min and max of the discrete set of points you are mapping to, you're going to use this formula when you use this asymmetric linear quantization. So for example, if we were using 8-bit precision, we will have -2 to 7, and then 2 to 7 minus 1, which would then give us this range that we kept seeing. Okay, so these are the first things we decide. Basically, if we look into this illustration, it's determining what are the ranges of these two intervals. Now, we need to determine how to scale these points on this blue interval to these points in discrete points in our red interval. So the goal is to find the optimal scale, like how do you scale these original interval, and 0 point to minimize our quantization errors by ensuring that the values fit within the target and integer range. Okay, so again, two formulas for how to do this. For scaling, we are just going to take what is the size of the quantization interval, which is 255 for 8-bit precision, and divided by what is the range of our full precision interval. And 0 point, we are going to calculate with this equation, and it's going to, once we do the scaling, it's going to help us shift the quantized interval such that we actually fit within the ranges. I will give you an example in a second here. Let me actually go immediately to this point. So imagine you have this set of, you put all of the numbers in your weight matrix onto the interval. You get an interval bounded by 2.5 and 8.3, so range is 5.8. If you would just scale it using that scaling equation, or the one that's going to come next, you would get something that's not within this interval of negative 128 to 127. So you just need to shift it by the 0 point to be placed within this interval. That's how it works. I have mentioned before, and I will use this example again, how scale determines granularity. Basically, how we scale will determine which parts of the original interval are all placed within the same point in the quantized range, which means that some, small interval within your large interval is going to, all those numbers are going to be placed to the same quantization integer. And that determines then this kind of precision error, right? Like the larger that number is, more values, more larger this little interval within the big interval is, that means that your granularity is larger and you will probably have, less precision per quantization integer. Okay, so we determined the intervals, we determined the scaling factor and 0 point. Now we need to use all of that. Before I give you, I'll just show you an equation for, how you then apply, scale every number in the weight matrix onto the quantization integer. I want to talk about this granularity a little bit more. So in my illustration so far, I keep saying, well, we have a single weight matrix and find minimum and maximum that determines that blue interval of full precision range. The issue here is when we have some outliers, right? If we have very high maximum, but most of the other values aren't so high, that's going to mess up the whole scale, because scaling is determined, but it's determined by the range, right? So imagine we have very high max, then all of these other values we are going to be placed to similar quantization points, and we will lose the difference between them that we care about. So typically we don't actually do per tensor quantization, rather we do things called per channel. Now, channel is just a technical term to refer to the output dimension of our weight matrix. So since we are using PyTorch, now you have length and breadth, the torsion and linear in this course, you know that typically we put output dimension, then input dimension. So the number of rows is going to be the channel here. Did I say it wrong? Is it the output dimension goes first in torsion and linear?
I think, yes.
Okay.
If I remember correctly.
Okay, yeah. So channel will be each row in our typical weight matrix that's produced, that we produce. And then instead of calculating one scaling point and one scaling factor and one 0 point, we are going to calculate them for each row in our weight matrix. And then we are going to do the scaling row-wise. And in this way, again, we are going to get integers, but not by applying just a single scaling factor on the entire tensor. And then we have finally, even that can cause issues. Even within a row, we can have outliers. So the most advanced, but computationally starting to become a concern solution is to also divide each row into groups. So you can, today dimensions can be like 4,000, say. You take a window of the size 100, or I should say segment of size 128. So now you get, I don't know, 4,000 divided by 128 number of smaller intervals within a row. And for each one of them, you compute the scaling factor and do separate scale. Can you imagine what becomes an issue now? I mentioned that now we are, and I think I've given away all the answers on slides. So again, no good slides. But what would be an issue with this per group quantization? In terms of memory specifically.
I feel like I'm cheating because I read the slide already, but the memory over it.
Yeah, go ahead.
Yeah. The memory, I mean, we have to store all of this scaling factor.
Yeah, exactly right. So it seems not such a big problem if you think in the context of just a single weight matrix, right? Single weight matrix you have for each row, so 4,000 rows, and then for I don't know, depends which weight matrix you're looking at, but it can be like hundreds or thousands of input dimensions. So for each row, you have a scaling factor, and then you divide them into these, additional groups, and each one of them has a scaling factor. That's a lot of numbers to store, these scaling factors for single matrix. But then we have many of those matrices, so this problem compounds. And the issue becomes that now you need to also record all these scaling factors. But what people will do is they will quantize the scaling factors themselves as well. So it's a double quantization. I know, beautiful. This line of work is just so elegant. Yeah. So double quantization is a thing, but this can give you a really good trade-off between accuracy and memory. It does take a bit more memory. If you do this double quantization, it kind of helps with storing all of that, but you get really good accuracy, and by accuracy I mean very low quantization error. Something like this matters more if you go really low, like 4-bit precision. It's typically done for that, but for 8-bit maybe is a little bit too much. So for 4-bit, you will certainly do something like this. 8-bit, you can get away with it. Okay, so again, just an equation for now you have your scaling factor and you have floating point. How do you map your original value W into a new quantized value? You use this formula. Yeah.
So I know you could use like complexity or accuracy to measure like how much information you're losing in this process. But are there any metrics where it's like, I don't know, like information loss metric, I guess you could call it, where it's like, okay, like we had this many number of unique values in our original weight matrix. How many of those unique values are now being mapped to the same quantized bins and like measuring that as like information loss?
Yeah, well, typically people will do, and I will come to that to the next slide, dequantization. So you take your quantized values and you turn them back into full precision, and then you check it, right? Which is, I think, more or less the same idea. Yeah.
I've been seeing a lot of these round functions here for these equations. Are we rounding up or are we rounding down?
That's a good question. I don't remember. I will check it. Yeah, yeah. Or we can see a next example, maybe, let me see here. I would actually, I think it's rounding, it's floor, because otherwise you can go outside of the interval. So I think if you have 2.1 were rounded to the upper value, you never want to go outside of the interval. So my intuition says it's a floor, but I need to check. I'm not sure.
Okay.
Okay, so for actually to store these weights, we are going to use these quantized values, right? So let me go to this example over here. So we start with some matrix. It's in a full bit precision. We are going to, in this example, we are going really low to only 2-bit precision. And this is how we store the model onto the GPU. However, when we actually, for a given batch of data, want to do computations, we are not working with quantized values. Rather, we take that batch, just a single batch of data, and for it, we are going to reconstruct the weights. And for reconstruction, we are going to use this equation. Okay, so I'm writing some notes here. I will admit that hardware is not my thing. I'm very bad at knowing hardware anything. But there is also a difference between what stays on to GPU memory, and there are GPU caches where computations can happen. So they are not really stored onto GPU memory, but they are kind of computed on the fly, which matters here when you do dequantization. Okay. Yeah, and this matters because, like, if we need to additional memory to store this dequantized value, we are kind of going into circles, right? But we are not coming in with this dequantization of weights. We are not in the same situation where we started with, where we need to store the full model in full precision. We can get away with not doing that. Okay, so here is a full pipeline. So we have full weight matrix in a full precision. Here example is with doing the quantization tensor-wise. So we are finding the minimum and max of the weight matrix overall. We are not doing per row thing, which usually we do. And then you get your integers, and then you dequantize. And to measure your quantization error, you can check the difference between your dequantized weight matrix and weight matrix you started with, and you can use some matrix norm function to compute how much difference there is, like Frobenius norm. Smaller the difference, the better quantization is. Yeah.
Like, see what I mean? So,
Yeah, but let's not do that. It doesn't have weights, right? So autoencoder is a neural network, right? So
right.
yeah.
I'm just curious if we.
Yeah.
Wait.
Yeah, you can think about it, but I just don't want to confuse anyone. So like autoencoders refer to neural networks that through weights of those matrices are producing encoded and decoded representations of something. And you are right. In a way, we are encoding the original weight matrix in this new weight matrix that has lower precision, and then decoding it into the original matrix. But different things. This
Yeah.
is not done through a learned method. Yeah.
Guess I was getting, like, if you're doing group norm, for example, already during your training Python, you're learning these like scale and shift parameters. Maybe you could learn some scale and shift parameters for quantization at the same time. It's kind of random, but I was just curious about.
Okay, yeah, I don't know whether anyone had tried something along those lines. That's, yeah, an interesting idea. Although I do like how simple this is also, right? You have like 4 equations and it works. So yeah, I'm admittedly, I'm not super, familiar with lots of things that are happening in the space, but I haven't seen something that have quite picked on. And probably because, here you have 4 equations with symmetric version, you have one less, so it's just a simple whole computation. Right. You don't want additional weights that you then need to store themselves, right? Like that becomes a problem too. Okay, as I said, linear quantization just assumes that your original data is mean-centered, 0 mean-centered. So you don't need that 0 point because you don't need to shift anything. Like your original data is centered around 0, your quantized data is centered around 0. So shifting it by 0 point is unnecessary. So equations are just ditching that term z, and everything is a little bit simpler. And of course, now knowing what we know, that weights can be 0 mean because we're using layer normalization and activation not, it makes sense to use asymmetric quantization for representations, activations, and the asymmetric one, symmetric for weights and asymmetric for activations and representations. But in reality, we don't do any of this because Hugging Face does everything for us. So we have a library called Bits and Bytes that's very well integrated into the Hugging Face's ecosystem. And in terms of your code bases, if you're just doing inference, almost nothing changes. The only changes you would need to your code, you would need to import Bits and Bytes config. You would need to make an instance of this class and say load in 8-bit true. And then when you are loading a model, you would load them as usual. You would choose your right auto class, such as auto model for causal LM, dot from pre-trained, name of your model, but then you would add this special argument, quantization config equals quantization config 8-bit that you just created. And it's going to load your model into 8-bit precision and do everything for you. You really don't need to then think about anything else once you have loaded it like that. So yeah, the Bits and Bytes won't do the tensor level quantization, rather per column or per token. And one extra thing they are going to do is they're going to actually check what are the outliers. So less than 1% of the, tensor. And those outliers are going to be kept in full precision, and everything else is going to be quantized. That's how they handle outliers. And then for 4-bit quantization, we are going to use per block. And we are going to do double quantization by quantizing the scaling factors themselves as well. So, just various tricks and things, but the core thing is using those 4 equations we have seen. Yeah, and I really don't see a reason why you would do the quantization, writing a script to do it when Bits and Bytes is so nicely integrated into Hugging Face. Okay, questions about quantization? Yeah.
Curious, so taking like the long with it, we take the biggest model, it's like 100 million, whatever parameters. Quantized version of that, is it better than full precision with less parameters? Is that like generally?
Today, when this works well, quantized version of a larger model is going to be on par to its full precision version, and therefore it's going to be much better than much smaller variants. Yeah. And as I said, 3 years ago, I would have a different answer for you. I would be like, no, like you need to figure out which point quantization is just not giving you benefits. But today, yeah, in my group, we just use it. Like we check what is the largest model we can place on the collective GPU memory when we use quantized version of that model. And then that's the model. Yeah. And these days, models are typically not released in excessive sizes. So for example, Alma 3, the largest version is 32 billion, I think. But you will still quantize it and do all of this because it's easier to get, when you are working with a shared resource like CHPC, it's much easier to get a single GPU than a node with 4 GPUs, right? So still, even though you might have resources for full precision, if you don't have dedicated resources, then just do quantization. Yeah.
So this kind of leads me to ask, like, if the model performs on par with same for quantized versus full precision, are people just training their models with less precision too? Because something will right?
Yeah, we are gonna fine tune smaller precision as well. But models are retrained in the full precision still. That's a great question. I mean, follow-up question, of course, is and then why? I guess I wouldn't know exactly why, but maybe just as brainstorming an answer here. It could be that you need to learn good representations and weights, and only then you can quantize them and go from there. Like doing everything from scratch might be too big of an effort. But yeah, it's actually a good question, but I don't know the full answer to. Yeah, and I'm wondering whether are they using 16 or 32-bit precision? That's another question. Yeah, I don't know. Need to check these details. Yeah.
I feel like the loss function would be kind of like blocky, I guess, like
Mhm.
screen. Like if you go to low precision, like your gradients would be not as well approximated.
Yeah, that makes sense. Yeah.
Yeah.
Although, like just because we are going to talk about how we fine-tune models that we are going to start from their 4-bit quantization with QLoRa and fine-tune it. Yeah, it's obviously it works for fine-tuning, but it took a long time to get there as well, right? So yeah, it seems like there is some benefit of having already good starting point, but I can't really tell you an argument for why. Yeah. Okay, so just to repeat, we want to use GPUs. They make everything faster, but to make the GPU memory, we need to change the precision of our models so we can fit them onto that, onto GPU memory. So, although we are trying to fix memory issue, I want you to remember that the goal is to have speed in the generations, right? And the speed we get comes from being able to fit the model and do computations on GPU. So just because we're talking about memory, don't forget that what we get out of handling memory well is speed, computational speed. Okay, so now, similarly, we want to get even more speed out of our computations. And for that, we can use something called KV cache. Without looking, what am I referring to when I say KV? Key and values, right, that we have in our attention mechanism. So remember, our transformer has a decoder block. The decoder block has a multi-headed attention. Each attention head consists of linear projection to keys, values, and queries. And now, when we train, I feel like at this point, we have repeated this so many times. We know we are using teacher forcing and we are tensorizing everything, causal attention handles everything for us, everything is smooth. At the inference time, we don't have any other options but then to do things sequentially, right? Like we start with the beginning of sequence token, we generate the token, that token becomes an input, we generate next token, that token becomes an part of the input, and so on. And so you need to now visualize how attention works, right? So when we are, here, okay, so we started with the BOS token and we have generated T1. Well, it becomes input, and then here we generated T2, and that becomes input, T3, and then T3 becomes input. Okay. And so let's say we are at the position T2, and we are trying to generate next token. So now, what are our keys and values? What are their shapes? The way I have, told you. We have as an X, we have tensor or matrix of the size 3 rows, right? For BOS T1, T2, and whatever is the dimensionality of the representations. And then we project this into key, query, and values, right? And we get the same shape, which is 3 by D. Okay. Now, the issue here is that when we get a new token, let's say T3 here, and we want to generate T4, if we are just linearly projecting this vector, as I told you, we are going to be recomputing the queries and values that we have already computed. Do we see that? Right? So we are using, don't forget that we have matrices WQ, W key, and W value. They are of the size D, let's call this DM, and then dimensionality of, like, let's call it DH for head, H for head, right? They are shared, right? Like, just because my input is now different, extended, I am not changing the weight matrices here. And remember that the product of this matrix X with this matrix, weight matrix, is basically linearly projecting each one of these rows independently, right? So just because now I have new row here, when I multiply this extended matrix X with this weight matrix, the first 3 rows of the output will be the same. So now you might kind of start to make connections. We are talking about efficiency. That seems wasteful, right? Like if I have already computed keys and values for the first, 3 positions, if I'm at the 4th position, I can reuse them instead of recompute, right? So that's a very simple idea and a very simple trick to, get some efficiency improvements. We are going to keep a cache of keys and values. And when we get a new position, T3 here, for example, we are going to create query matrix only for that input vector that corresponds to T3. Okay, so not entire stack of rows corresponding to all input tokens, only for that one will be our query. And we are going to reuse the values and keys. Sorry, we are going to calculate keys and values for it too. That's clear. I just wanted to say we don't need query matrix for this whole thing. Yeah.
Yeah, I was wondering why aren't we caching the previous queries in addition to these?
Yeah, right. That's a good question. So remember that when we have attention matrix, it's basically the product of queries and pieces transposed. And what we get is that matrix of the sequence length times sequence length, where each row corresponds to token in the input. So token, I will use the same notation as I had before. So BOS, token 0, token 1, and so on, right? And here we have attention scores, which tells us how much other tokens in the input are important to that one, and we have causal here. And when you think about it, when we are at this decoding step, what we care about is how important are these tokens to this one. We no longer care how much these tokens are important to this one and how much this one is important to this one, right? We are trying to see how important tokens, other previous tokens are to this one, and then based on that, change the representation of this token, because eventually we will have final representation of that token, which is going to be multiplied with our language model in hand, which includes that matrix of the size of the vocab times dimensionality of the model, right? So, long story short, when we are doing this decoding sequentially at the inference time, next token prediction is done based only on the last token's representation. So you don't need the full attention matrix. You need only a row corresponding to that token, right? So this one, right?
And that row is going to be based off of the queries for that.
Yeah.
And we don't need all the other queries because we
Yeah.
don't care about those previous.
You are
tokens.
exactly right. So
But then we would recompute all the keys because it's gonna take all that information from
Mhm.
above.
yeah.
Okay.
Yeah, so I could have, put all the queries and all the keys and get the attention matrix, which is square in sequence length. But I don't need all that information. I just need a final row of that matrix. So what I can start with is, instead of query, which is of the shape sequence length times d, I can start just with the query, its last row of this matrix. So just the last row and multiply it with this set of keys. And then I will get again just the last row.
Okay.
So it wouldn't be wrong if I had done all of this, taking the last row and so on. It's just waste, right?
Right.
So instead, I can start with only the key for this token, so single vector, multiplied with the matrix, where I store all the representations of the previous token and the current token. And then I will get importances of all the tokens, including current tokens for the current token. And then I can use that to update the value vector of this.
Okay.
Yeah. Remember, for values, I'm going to need all the previous values because that's the point of contextualization. I'm mixing and matching information from other vectors. So I need full query matrix, full key matrix. I need full value matrix, but I don't need a full query matrix. I can get away with the single vector. Okay, so we're going to now combine another idea before I present the full KV hash quantization. And that's so embrace this idea. We want to store query keys and values. I don't know what happens to my brain that every time I see a key, I say queries, but we want to remember store keys and values in some cache because we are reusing those computations. But the issue is that now memory for those vectors can also become large. So here is within the entire transformer, if you want to generate the next token, how much memory you need for that one token, one position in generation within the transformer. So we have, two, because we have keys and values, number of layers, number of heads dimension, and how many bits of precision we want. So precision bytes, not bits. So precision bits divided by 8. And if I plug this formula for a 70 billion model, it turns out I need like 2.65 megabytes per token. And although that doesn't sound dramatic because I have just talked about hundreds of gigabytes, this is just for a single decoding position, right? So if I have a lengthy sequence, a single token with 2000 generation steps, now this memory becomes 5 gigabytes. And now you know how many users of ChatGPT there are there are, I think, billion like weekly or something. Your OpenAI as a provider is certainly going to do generations for multiple users at the same time. So now let's imagine there is 100 users prompting ChatGPT at the same time, same model. Then we collectively make a batch of 100 inputs. And now this becomes, we multiply this value and this becomes very large. So for, let's say, serving 16 people at the same time, you would need to generate the sequence, you would need 86 gigabytes of memory, a full A100 of 80 gigabytes, which is, trust me, expensive. So we need to also save memory by saving all of these computations. And this is where, again, quantization comes into a place. So what KV cache quantization is marrying these two ideas, right? So we want to speed up computation especially for longer sequences by caching keys and values that we are reusing anyway. So why recompute them and waste time? But at the same time, we also want to speed up computation by having more GPUs at disposal. And we can do that by saving some memory through quantization of keys and values. So everything together, you will have, you just have a little bit funky interplay between what's quantized and what's not quantized. So bear with me. We start with query, key, and value for new token, right? So this is going to just be a vector now because new token is just a single vector. And we are going to start with a higher precision like float 16. We are going to quantize key and value of this newly created token and compute their scale factors. So we are doing per token quantization as well. And then you are going to add quantized key and value into a cache. So this is about building the cache part. So everything is quantized. And now you move into, all right, I save my everything into cache, but now I want to actually compute attention scores and values for this vector. So you are going to dequantize all cached keys and values for computation. You are going to get your attention scores. You're going to compute new values, new attention, and then, here, this is to say attention output of the mechanism, not the attention scores. And when you do all of that, you're going to get new representation for your current token based on which, after a while, you are going to make the next token prediction. Okay, so this is going to speed up inference and it's going to especially be relevant for the long text generation. So I think it's a little bit daunting when you start reading about maybe cache quantization because it sounds, I don't know, I feel like first time I was reading about it, no one explained it to me, so it sounded too fancy. But it's really simple. It's just about, all right, we would, because we are doing everything sequentially, we would recompute certain values and keys, and we don't need to do that. So let's be smart about what we are caching. Also now we know that quantization works, so why don't we save also memory and therefore have more GPUs at disposal, which directly means, faster computations as well. Okay, I don't have a Hugging Face snippet here, but I'm sure Hugging Face also handles caching for you too. Now, all of this was how to be faster at inference, right? Like we have trained the model and we want to generate tokens as fast as we can because we are either impatient researcher or you need to, give outputs to people. Now, I started today's lecture by saying to you that as long as you have data, you should most likely fine-tune your model because you are going to most likely get the best performance for the specialized tasks you care about. And nothing I said about efficiency was about efficiency of fine tuning. And that's going to be the topic we're going to talk about next. I'm going to talk about one method and a kind of enhancement of that method for how to do fine tuning that we use extensively today, QLoRa. And QLoRa, that method, is part of a larger family of methods that we call PEFT, or parameter efficient fine tuning, which basically all these methods work on the principle that instead of fine tuning the entire language model, we fine tune only limit the number of its operations, very often feed-forward layers, because those change the most with fine tuning we have observed empirically. This is a screenshot from a survey from last year, so probably mega outdated today, but you can see there is a lot going on here, right? So it's a quite active area of research, but I can tell you that QLoRa has been used super extensively. Okay, so just to be clear, I'm going to teach you one little box here out of all of these. Okay, now, I'm trying to be really ambitious here, I see, and explain LoRa in like 4 minutes, but here we go. We can come back to it if it wasn't clear, but how LoRa works is by reconstructing a low-dimensional reparametrization of the weights. And because we are doing the low rank reparametrization, we are going to have less parameters in the reparametrization. And then when we fine tune reparameterized version, we are just fine tuning less parameters because simply there is a less of them. And that's how it works. Okay, let me see. I'm gonna go directly here given the time. Okay, so how many of you are comfortable with the rank of a matrix? Do we all remember what that is? Yeah. Okay, I see enough notes for me. I have learned that I have started to teach, and I just assumed everyone takes linear algebra first in the first semester, and only this year in my 4th year of teaching. And my husband teaches linear algebra. I was like, so when do you teach that? He's like, oh, like 4th semester. I was like, what? And I kept saying to my students previously, oh, you know that's something you have learned, you know, in high school. So now I'm more cautious and I check whether these terms are familiar to you. So rank of the matrix is the maximum number of linearly independent rows or columns in the matrix. So I wanted to ask you this. I keep giving away my answers. What is the rank of this matrix? It's 1, right? We can see that every column here is scaled version of the first one by the value in the first row. So it turns out that the weight matrices are also low rank, and we have empirically found that. And then creators of LoRa had made use of that observation. So there is a number of papers you can read that shows that almost every weight matrix in a transformer architecture is low rank. So we can make use of that. First, what we are going to do is rank decomposition. We are going to express our weight matrices as the product of matrices that have shape number of rows of the original one times the rank of that matrix. And another matrix of number of rows is going to be the rank of the matrix times the number of columns of the original one. So because our example matrix had such a low rank, that means we are going to make the product of just 2 vectors. Okay, now key observation here is that here our original matrix has 25 values, and one of these matrices that we use in decomposition has only 5. So the number of values that we need to store to represent the matrix with this product is fewer, right? And that's the point, right? That we have from 25 values we need to change. We can now change fewer number of parameters. And because we need to train less parameters, everything is going to be faster by direct consequence. Okay, so, all right, 1 minute. This is LoRa. It's really simple. So you start with your pre-trained weight matrix. It's low rank. And we are going to represent the fine-tune matrix as the sum of the original one plus some difference, right? We are changing the weight, so we can always do that. And we are going to assume it's this fine-tune matrix, we are going to assume it's low rank one as well. This is not a crazy assumption because empirically we can also see that. We are going to choose a hyperparameter R, which is kind of a hyperparameter that serves as a rank of our original matrix. We are going to have a matrix of the shape R times D coming from that notion of rank decomposition, initially randomly initialized and another one initialized with zeros. And we are going to try to decompose the difference as a rank decomposition of these two matrices. And the parameters we are going to change are parameters of A and B, which collectively are fewer than we had in the original weight matrix. So because we need to change less parameters, everything is going to be faster. We also need to store less things. Okay, so we're going to continue. I'm going to tell you a little bit more about how optimizers also require a lot of memory. And then we are going to talk about QLoRa, which is yet another additional LoRa to make everything even faster. Okay, have a great Thanksgiving break. Again, thank you so much for being here. Yeah, eat a lot of food and sleep a lot and take a proper break. And then we're all going to be super fresh on Monday.